All right, so we got ourselves one last example of static equilibrium. And that's what's in the little floating cloud of principles up here. Static equilibrium. Take your forces in the x direction. Add them up. They equal 0. Take your forces in the y direction. Add them up. They equal 0. Take your torques. Add them up. They equal 0. We're going to apply that to this problem here. What we have here is a flagpole with no flag. Sticking out the side of a building. Maybe they're cleaning the flags. Flags aren't around. We've got a flagpole with no flags. And before I pose the question to you, let's look at the forces on this flagpole. The yellow flagpole right there. Let's look at the forces on them. Well, it's got a length of 1.5 meters and a mass of 2.0 kilograms. So it's got a mass, so it's got a weight. So right there, the center of mass, mg, right there. That's one force, the weight of the flagpole itself. Okay. What's another force acting on it? Well, there's the tension in the cable. We got a cable right here, 40 degrees. The angle's 40. I made it maybe a little bit less than that, but let's say it's 40 degrees. So we got a tension, right? That cable is pulling up on the flagpole that way. So there's a tension running along that cable this way. Right? That's the only direction the tension can possibly pull on it, is along the cord, right? So there's a tension that way at an angle of 40 degrees. What other forces are on it? Well, down here at the end there's a hinge. Okay? There's going to be some forces on the stick from that hinge. Okay? Now, obviously one of the forces is this way because there's a contact force, like a normal force, pushing it out this way. Right? So there's going to be a force. I'm not going to call it normal force. I'm just going to call it a force in the x direction. So there's going to be a force here, F sub x. And there's also going to be, as we will see, a force up at the same point. In other words, there has to be another force acting up on it there. Else the flagpole would slip down. Okay? Well, if there were no friction or no contact forces of any kind in the y direction, the flagpole would slip down. So there's going to be another force up this way. We'll call it F sub y. Okay? So those are the four forces. And actually, F sub x and F sub y could be two components of a single force. Okay? That will point up this way somehow. So there's really only three forces, but this last one here we put into two different components. All right? And we'll see in a minute why there have to be forces Fx and Fy here. But let's just say for the sake of discussion that they are there. Here's what we want to know. We want to know what the tension is. We want to know what F sub x is, and we want to know what F sub y are. We want to know those three things. That's what we're asking for. The tension, F sub x, and F sub y. We're going to find out what they are. We're going to use this. All right? So let me pull out my yellow, say, and let's get to it. We're going to apply the first one first. Sum of the forces in the x direction is 0. Sum of the forces in the x direction is 0. Well, what are the forces in the x direction? Well, there's F sub x, right? The force of the wall on the stick this way, or of the hinge, on the hinge really, this way. And so that's going to be just plain old F sub x. And then there's going to be, has to be another force acting back this way on it, because those forces all have to add to 0. Right? The x forces have to add to 0. So we've got F sub x pointing to the right, so there's got to be another F force pointing to the left. What do you think that is? Well, it's the x component of t, right? T is off at an angle. So, this is it. You know, my red's looking for. And so we have two components of it. We have an x component here that points to the left, t sub x, and then we're going to have a vertical component also, t sub y, right here. We have to resolve this into its two components. T, I mean. We have to resolve t into its two components. So we got f sub x minus t sub x equals 0. But what is t sub x, right? X is the adjacent to the angle. So this is going to be f sub x minus t cosine theta equals 0. And there are two of the things we're looking for, f sub x and t. Right? We're looking for, what we're looking for is, let me put them down here. So what we're looking for is t sub x, f sub x, f sub y, and t. We want to know those three things. That's a little dark down there. F sub x, f sub y, and t. That's what we want to know. And two out of those three things are in this x equation, but we can't solve for them because there's two unknowns, f sub x and t, in one equation. So let's write another equation. Okay, so that's our x equation right there. Let's do our y. Sum of the forces in the y direction equals 0, right? That's our second. So we've done number one, gotten everything we can get out of number one. Now we're going to go to number two. Sum of the forces in the y direction equals 0. Well, let's see what we got. Looks like we have two forces up in the positive y direction and one force down in the negative y direction. So we're going to have f sub y is up plus t sub y is up minus mg equals 0. Okay. But t sub y, right, this is a little rectangle here. T sub y here is the same as that, the length here is the same as the length there. That's the opposite of theta. So this is going to be f sub y plus t sine of theta minus mg equals 0. And that is our y equation. Now look, we have 3 out of the 4 things. We have all 3 things now. We're looking for f sub x, we're looking for t, we're looking for f sub y. And there's t again. Okay. Now we have 3 unknowns, f sub x, f sub y, and t, but only 2 equations. We need one more equation. And that's where the torque comes in. So this is all of our x here. This is all of our y here. We've now done the second equation. Okay. And that's all we can do with those. We're done with those. We can't go any further because we've got 3 unknowns but only 2 equations. So we need a third equation. Boom, there it is. Sum of the torques equals 0. Now, when you sum your torques, what do you need to do first before you sum your torques? You got to pick an axis. That's right. I heard you say it. You got to pick an axis. And let's pick this axis right there at the hinge. Why? Because we have 2 forces going through that point. We have f sub y and we have f sub x. Right? So neither one of those forces, f sub x or f sub y, is going to create a torque because they both pass through the axis. So if we pick that as our axis, we can ignore fx and fy in this equation. We can completely ignore them because they don't produce torques. So fx and fy produce no torque around that axis. Around that axis right there. Because they pass through that point. Okay, so what we got here. We're going to have two forces acting. We have T acting, right, which we're looking for, and we have mg acting. Those are the only two forces left when you ignore Fx and Fy. Because those aren't going to produce torques. Only T and mg are going to produce torques. And we're going to treat T as a single thing. We're not going to worry about its components here. So we really only have two forces, mg down and T up. Tx and Ty are just part of T. So we're just going to look at mg down and T that way and forget about T's components for right now. We had to worry about T's components when we did this, the x and y equations. We don't have to worry about them now. Remember that the torque is F R sine of theta. So we have to do what we did in the last example. We have to apply this for every force. And we know that because R is 0 for Fx and Fy, just another way of saying what I just said a moment ago, because the moment arm is 0 for Fx and Fy, we can ignore those. They don't produce torques. R is equal to 0, so the torques produced by Fx and Fy are 0. So all we have to worry about is mg and T. Which one creates a positive torque? T creates a positive torque because T, if we hold this in still, T tends to pull the rod in a counterclockwise direction. So what is the torque produced by T? Well, it's the force, which is going to be T, times the magnitude of the lever arm, which in this case is L, the length, right? L is 1.5. This is our length L. So the moment arm now between the axis, remember moment arm is the vector between the axis and the point at which the force is acting. And tension is acting at the opposite end of the stick, of the flagpole. So it's going to simply be TL times the sine of the angle between them. And what's the angle between R and T? Right? Between R and T, between the R and the force. Here's R here. I didn't draw R. It's too complicated to draw. But R points from the axis to here. And then T is up this way at 40 degrees. So it's TL sine of 40. That's the torque produced by T. And then we have to think about the torque produced by mg. Minus mg, that's the force, that's F. What's R now? Well, it's halfway out. It's a uniform rod, it's a uniform flagpole, so the center of mass is at the middle of the pole. So that's going to be L over 2 times sine of what? Right? The moment arm is going to point from the axis to the center of mass this way. Mg points down, so that's going to be 90 degrees. So that is the mg L over 2 sine 90 is the torque produced by the weight of the flagpole. Sine of 90 is 1. So what we get is TL sine 40 minus 1/2 mgl equals 0. Okay. I just pulled the 1/2 out front. L goes away. Doesn't matter what L is, it turns out. Does not matter at all. L could be a ½ mile. Doesn't make any difference. Okay, so T times sine of 40 equals 1/2 mg. Plug in your sine 40, plug in your mass of 2 kilograms, plug in your g of 9.81, and you get the tension is 15.26 newtons. Or we could rewrite it as, where's my eraser here? Tension is, with the correct number of significant figures, 15 newtons. T is 15 newtons. Okay. Now that you have T I'm not going to take these steps. You can do this. This will be the exercise for the student. Now that you have the value of t, 15.26 newtons, you can plug them into the into the y equation here and into the x equation there. And when you do that and solve for f sub x and f sub y, we'll get f sub x should be equal to 11.69 or 12 newtons, and f sub y is 9.8 newtons. Again, all you do is you take this 15.26, you plug it back into your x and y equations, okay, and solve for fx and fy. All right? That's it. See you next time.